Hi all. Okay, so this week's video is going to be about memory corruption vulnerabilities. So this video is we're going to take a broad overview of memory management vulnerabilities and give you some examples. So we're going to be taking a look first at just broadly at memory management vulnerabilities. Then we'll be looking at different categories of attacks, ways of preventing memory vulnerabilities, and also methods of detection. So, as you're well aware by now, some languages are considered memory unsafe. So these are languages like C and C++, and these types of programming languages are designed in a way that give the responsibility of managing memory to the programmer, rather than having the framework itself or the technology surrounding the language manage it. So things like, so examples of automatic memory management is pretty much most of the high level languages that get used today, things like Java, C, in enterprise, things like Java, C#, JavaScript. They all use automatic memory management, so you don't have to worry about freeing up pointers or references that you've used in order to make space in memory. It's automatically done when you stop using. Like in a lot of these cases, they have some thing called a garbage collector, which runs and detects when a particular object's no longer in memory is no longer being used, and it'll just free up for you. So one of the advantages of having that is you're not going to necessarily suffer from memory corruption vulnerabilities, but a disadvantage is that it's requires more code, it's a bit more bloated, it's more resource intensive, it's not as fast, it's not as suitable for systems level programming. So usually, like most systems level devices are written in, like the device drivers and stuff, all written in like C, C++. So we're actually going to be focusing on in this module, pretty much we're just going to be focusing on the memory unsafe languages, so things like C, C++. We're looking at assembly. It's less common, but it's still possible, as I mentioned in a previous video, that you can still have memory corruption vulnerabilities in these other languages if you're running native code. So you're actually able to run native C code or assembly within Java and C# and some other languages like Objective-C. So you could technically still run into these problems there, but the usual standards like make it more difficult to write memory unsafe code. So managing memories correctly is important because mismanagement leads to two different problems. So if we free memory too early, so let's say we can end up with dangling pointers. So let's say we have a pointer to a memory object, we free it, and then we use that pointer afterwards. We're going to get some unexpected behavior, undefined behavior. Technically, within the language standards, they all say that mismanaging memory problems is technically undefined. If we don't free it on time, the opposite problem. If we're keeping objects in memory for longer than we need to, we'll have a memory leak. We can have a memory leak. So you might be familiar with the idea of a memory leak, which happens in programs where sometimes you'll see that that a particular program's like eating up tons of resources, and over time it's like just taking up more and more resources. That's usually a memory leak problem. So managing memory, it can be difficult, and it's obviously the source of a lot of software vulnerabilities. So yeah, when a memory mismanagement problem is when it's considered, they're usually considered undefined, like I say, and that means that the actual implementation can vary based on things like the compiler implementations, and the difference between different compiler implementations and like this area of undefined behavior, it can be a rich source of vulnerabilities. So there's two types, really. It gets split into spatial vulnerabilities and temporal vulnerabilities. So spatial vulnerabilities are problems like buffer overflows, where we're actually indexing into some piece of memory that's out of bounds, that we're not supposed to have either read from or written to. So things like buffer overflows, format strings, things like that. And so temporal vulnerabilities are what I was describing before. So it's all time-based. So if you actually mismanage memory across time, so you have an object that you have freed up, so like use after free is the example I was getting at before. So when you've actually used the dangling pointer, i.e. a pointer that's pointing to some location in memory that you no longer have an object in, and you dereference it. So yeah, that's a use after free vulnerability. An example of this is that old man bug from the first lecture first video, the Pokemon Red and Blue problem. That was a use after free vulnerability, and that problem actually occurred because they used the object for representing the player. They replaced the name of the player with the old man, and then they left. There was a design problem basically where they used the same memory location for two different objects at two different times, and the programmer didn't expect that you would ever be able to run into the issue of. I think the actual problem was that when you were trying to catch a Pokemon, it used a similar type of it used a similar memory area for something different. It was like a percentage chance of a certain Pokemon spawning or something. You can read up the details anyway, but yeah, these types of problems can cause real issues. Okay, so looking at attacks, different attacks. So we can categorize these in a few different ways. So code corruption attacks are ones which I have just been explaining. So it allows an attacker to control the instruction pointer or program counter, depending, so EIP or RIP in assembly in x86 or x64. So yeah, basically the register in your CPU that determines which instruction is going to get executed next. So you can, if you hijack that, you can redirect control flow to some other piece of some other part of the program that you want to run. So code injection is things like a buffer overflow where an attacker supplies their own code. So we can write some assembly instructions that would spawn a shell, so shell code, and we could place that within our buffer. That'd be a code injection attack, technically. Or we could also use code reuse attacks. So in modern day, we'll be taking a look at this in a couple of weeks. We're looking at return to libc, which is also known as return-oriented programming, which is a way of using the binary's own code rather than supplying some shellcode. So there are functions. So you basically build up a stack with different. You build up a chain of function calls using the instructions that are already within the binary. So it's called return to libc because you can actually return into the libc, into the instructions within the libc library, and then start running that code. So it's really hard. It's much more difficult to detect this, obviously, because you're not actually passing any external shell code, any external code in. And these kinds of techniques can be used to avoid most of the memory protections that have been put in place. There are some things that look at specific techniques that within ROP to try and detect things happening, like when it's, we'll get into that anyway. But yeah, there are some countermeasures, but ROP chains are quite difficult to detect. So next we've got information leaks. So information leaks are useful to bypass some of like the memory protections. So you can sometimes use two vulnerabilities, two different vulnerabilities in combination. One to reveal some information about the program that you're exploiting, and then another to then use that data. So you might like want to find a memory where a particular thing in memory is. You might have a format string attack that you can use, or something like some other vulnerability that doesn't like directly give you a control flow hijack. So like something like type confusion or use after free. So type confusion would be like if a program is accidentally using two different sized variables, you can sometimes make a, like, you can abuse this to extend a buffer so that you can read more data, for example. You could find some useful information from one avenue and then use it in another. So you might find a memory address of something that you actually, like a variable that you actually want to change. You might have some more limited a vulnerability which has more, like, some limited exploitation potential that you just use them in combination. And then data-only attacks are things which allow an attacker to modify some data within the program's memory space that we shouldn't be able to, according to the actual, like, implicit design of the program. So an example of this could be, we could corrupt memory in order to change our UID to another user's, maybe an admin's or something. So it could like lead to increased privileges or break access control policy. So preventions. Okay, so main way of preventing. So yeah, language security has come on a long way. A lot of these problems have actually been technically solved. Not all of them, but there are theoretical and even practical, like, different environments and programming languages that actually just take the manual memory management away, like C#, Java. They're popular in enterprises because it takes away all that headache, and those businesses are happy to accept the increased bloat and the increased resource cost of using a more memory expensive program or memory or resource expensive in programming language or environment. So there's been an example of this is Rust. There's a language called Rust which has gained a lot of popularity as, like, a systems level programming language, and they claim to have eliminated a bunch of memory corruption vulnerabilities by, they don't actually use a garbage collector, they have a different approach where the compiler does some clever things to try and figure out whether there's memory unsafe code before it even compiles binary, and it'll throw errors and not let you compile if it thinks it does some, like, static analysis stuff to do that. Okay, so fat and smart pointers. So just quickly on Rust as well, like, it's not perfect. There are still memory corruption vulnerabilities being found in Rust, so it's come a long way, like, and yeah, there's some papers around that I'll link to in the description, which is quite interesting. So fat and smart pointers. So we know that a pointer is just a variable which contains a memory location that when you dereference, you actually, like, look at that memory location. So fat and smart pointer are things like they contain more information than just a memory location. They have some information about the pointer that will ensure that it's used correctly. So they might have things like the actual data type of the thing that's being pointed to, like, included within the pointer to try and ensure that it's not accidentally used incorrectly. Coding standards and rules. So yeah, there are really good. So a good example, I guess, of this is the C++ core guidelines. So C++ core guidelines give you some guidance on how to write modern C++ without actually having to use pointers at all. And pointers, as we know, are the source of quite a lot of vulnerabilities. So this helps a ton. I'll link to that as well. Okay, so detections. So static analysis, as I just mentioned, is an analysis of the code at rest. So an example can be seen in, like, compiler warnings. They're not all related to security. They're not always related to security issues, but basically a compiler is doing some analysis on the code before it actually runs to try and pick up common problems. They can be they often pick up things like in this example, there's incorrect use of types being picked up. So dynamic analysis is, as you know from last week's lab with fuzzing, you're actually testing the program at runtime by with fuzzing. We're passing in loads of machine generated input to try and cause the program to crash and try and pick up, like, hard to spot errors. And yeah, that's memory corruption. Here's I'll add a couple more references. No, I think this. Yeah, I'll add a couple more to to the description. But yeah, cheers.